Most people are familiar with the term current when we see water flowing in a river or stream. We can tell the difference between high current and low current by watching how fast the water moves. Really, what we're measuring with our eyes is the flow rate, how fast the river is moving. It can be difficult to accurately measure the current in a river, so let's look at something that we can control a bit more easily: water flowing in a hose or pipe. If we want to measure the flow rate, or current, of the water in the hose, we can add some sort of sensor to the end of the hose. The way that we measure the flow rate is to determine how much water flows out of the hose within a certain amount of time. The units that we use for that might be something like gallons per minute or liters per second, but in any case, it will be some quantity divided by a certain amount of time. If we wanted to be extremely accurate about measuring the flow rate or current of the water through the hose, we could look even more closely. Here, we can measure the actual number of water molecules that flow past each second. Now, instead of measuring the current in gallons per minute or liters per second, we can measure it in terms of water molecules per second or minute. All of these are measures of current, just using different units. You can pick whichever unit best fits your particular application. Now, this concept of current can be applied to electricity too. Electrical current can be measured by counting the number of electrons that pass through the wire every second. However, for most applications, counting the number of electrons per second isn't a very useful way to measure electrical current. Just like counting the number of water molecules per minute isn't very useful when you're trying to measure the water current through a hose. For water current, we use larger quantities, rather than counting the number of molecules per minute. For electrical current, we can do the same thing, but electrons aren't going to be measured in gallons or liters. We are interested in electrons because they have electrical charge, which has an SI unit of coulomb. Each electron has a negative charge of approximately 1.6 by 10 to the 19th power coulombs. So, when we have a large quantity of charge flowing through the wire, we can simply measure the number of coulombs per second rather than the number of electrons per second. The base unit that we use for electrical current is an ampere, named after André-Marie Ampère, a self-taught French physicist and mathematician. The relationship between amperes, also called amps, and the current that we measure in coulombs per second is 1 amp is equal to 1 coulomb of charge moving past a point each second. Symbolically, we use the letter I to represent electrical current, and the letter Q to represent charge. We can formally define electrical current as the time rate of transfer of electric charge across a specific cross-section. Now, we've defined electrical current as the time rate of transfer of electric charge, but we haven't given it a direction yet. When we look at a river, it is obvious to see which way the water is flowing, so we can easily point to the direction of current. But electric charge can be either positive or negative, and we want to distinguish between the flow of positive charge over time and the flow of negative charges over time. When electricity was first being studied, it was found that there were two types of charge carriers. When there were equal amounts of both types, then it would appear as though they canceled each other out. So, Benjamin Franklin coined the terms positive and negative to describe the two types of charge. Today, we know that if we have an equal number of each type of charge, the overall charge will be zero. However, when describing electrical current, the concept of protons and electrons was more than 150 years in the future, so an understanding of what was actually moving was not understood. Benjamin Franklin made the choice to say that electrical current, or electrical fluid as he called it, moved in the direction that the positive charges flowed. What we know today is that for most electrical current, the only charges that move are the negatively charged electrons. The positively charged protons are inside the nucleus of the atom. So, if we can identify the direction that the electrons are moving, we know that electrical current is pointing in the opposite direction.